Let's look at section 8.6, which is solving rational equations and inequalities. We're going to first focus on equations. So a rational equation is simply an equation that contains one or more rational expressions. So we can have something as basic as x over x plus 1 plus 7 equals 9. So here we have one rational expression and a few constants. It's still a rational equation. We could have something more elaborate like x plus 1 over x squared minus 2x plus 3 plus 7 over x equals 19 over 2x squared plus 4x minus 3. Again, more elaborate, we have multiple rational expressions, but it's still an equation. And lastly, we may have something like this. X over 5 equals x plus 3 over 10. In this case here, we have two rational expressions, and it's still an equation because of the equal sign. Remember, something like this we call a proportion, and you can cross multiply in that case. Okay, so again, lots of examples of rational equations, but the main thing is you have to have at least one rational expression. Remember, that's where we have some variables in the denominator or numerator. All right, so let's go into solving rational equations. To solve rational equations, it's really important that we factor our denominator and we find the domain. If you don't do this, you may have answers that are incorrect. Okay, so in the past, sometimes this has been optional, but you must factor and find domain. Step 2, we're going to find that LCD, but this time instead of writing each fraction with the LCD, we're going to, with step 3, multiply through by the LCD. What happens is when we simplify in step 4, it will cancel our fractions out. Now we will have either a linear equation or a quadratic equation to solve, and we'll go ahead and solve that equation. However, you must check for extraneous solutions. So let's look at an example or two together. So for number 1, pretty straightforward, not much going on. We don't have to factor our denominators, but my domain is going to be where we set x equals 0. So my domain is everything but x can't equal 0. Okay. Step 2, we find our LCD. We look here, we have x and 3, so my LCD is 3x. What I do with that LCD now is I multiply the entire equation by the LCD. Excuse me. So I multiply by 3x. Remember, every single thing needs to get multiplied by the LCD. So if you need to show that you're doing it on both sides, go ahead and do so. Or again, the parentheses will remind you to multiply through to everything. Now, when we do that, we could literally multiply across, or we can just start to simplify. So if I multiply 3x by 2 over x, I'm going to have an x up top and an x on the bottom. So I'm left with 3 times 2, which is 6. That denominator is gone. Now, plus, when I multiply 3x to the 5 over 3, we'll have a 3 up top and a 3 on the bottom. So I'm left with x times 5, which is 5x. And lastly, to the right-hand side, when I multiply by 3x, x up top and x on the bottom will cancel, so I'll have 7 times 3, which is 21. Now I just took this rational expression with fractions and made it become a linear equation. So pretty straightforward. We just get x alone, and we get x equals 3. So now we check. If I look at my domain, is it okay for x to be 3? Yes, as long as it's not 0. Any other number will work. Okay? I'm going to now go on to number 3. So for number 3, we're going to factor our denominator. So the first one is factored, but the second one is not. And so that allows me to find my domain. My domain, if I set the first one to 0, I would get -1. And then if I look at my second fraction, I would get +1 and -1. And then the last term doesn't have a denominator, so it's okay. So my domain is x such that x cannot be plus or minus 1. Now, what's the LCD? The LCD will be x minus 1, x plus 1, right? There's an x plus 1 that shows up twice, but just once in each fraction. So we only need it once. Then we include the x minus 1, and again, that last term doesn't have a denominator. So I'm going to take that LCD and multiply it through to the entire equation. When I multiply it to that first fraction, we will have an x plus 1 up top and an x plus 1 on the bottom that will cancel. So I'll be left with the 3x that was there and the x minus 1. When I multiply it to the second fraction, the numerator of x minus 1, x plus 1 will cancel with x minus 1, x plus 1 in the denominator, and simply just 12 is left. And then when I multiply it to the last term of 2, since there is nothing in my denominator, nothing will cancel. So we have 2 times x minus 1, x plus 1. Fractions are gone. Now we distribute and solve. So I'll have 3x squared minus 3x equals 12 plus 2 times x squared minus 1. Now we'll continue distributing, so we'll have 3x squared minus 3x equals 12 plus 2x squared minus 2. Here we have quadratic, right? So we need to make sure to make this equation equal 0. So we'll bring everything over to that left-hand side. When I subtract 2x squared, we get x squared. We'll have minus 3x, and then we have positive 10 on the right, so that'll give us minus 10. At this point, we'll factor. So I will have x minus 5 and x plus 2. This gives me two solutions of x equals 5 and x equals negative 2. But we need to check. Are those okay? Yes. The domain said we just can't be 1 or negative 1. So both of those solutions are okay. So sometimes you'll see it circled like that. Otherwise, they'll write it as a solution set. Remember, this is not an ordered pair. This is a solution set. If one of those does not work, then we would cancel one of them out and just circle one answer. And maybe both of them don't work, and in that case, it would be no solution. I'm going to have you try number 2, 4, and 5. Okay? Now let's look at rational inequalities. So the beginning of this will be very similar to what we just did with equations. However, we have a little bit more work at the end. Okay? So let's start with number 6. With number 6 here, we're going to make sure to factor our denominators. Okay, everything is factored, so I'm going to find that domain, and our domain is that x can't be 2. Okay, so what that means, remember again, is that an excluded value is 2. Okay, the other denominators are constants, so we don't have to worry about them. Now let's find our LCD. So the LCD here will be, we have a 3 and a 4, so that least common multiple is 12, and then we have x minus 2. Okay, so again, step 1, factor the denominator, find those domains, find the LCD, that's what we just did. So now we're going to multiply everything through by that LCD. When I do that to the first fraction, we will have 12 divided by 3 gives me 4. We still have the x, and then I also have x minus 2. For the second fraction, the x minus 2's will cancel, but I'll have 1 and 12, which is simply just 12. And then for the last one, we will have that 12 divided by 4 is 3, and then we still have x plus 1 and x minus 2. At this point, you can sort of pretend that this is just an equation right now. So if you want to ignore that less than for now and make it just be an equation, that's okay. At the end is when we'll go back to make sure we really reinstate that inequality symbol. So now at this point, we're going to just solve and distribute. So we'll have 4x squared minus 8x minus 12. Again, you can just pretend it's an equation for now. equals 3 times, this will be x squared minus x minus 2. Keep on going. So we have 4x squared minus 8x minus 12 equals 3x squared minus 3x minus 6. Again, at this point, it's a quadratic, so we're going to move everything to the left-hand side. When I subtract 3x squared, we get 1x squared. I'll add 3x, that gives me negative 5x. And I will add 6, which will give me negative 6. Here I will now factor, right? What multiplies to negative 6 and adds to negative 5. Be careful here. Oftentimes 2's and 3's trick us up, but it's a negative 6 and a positive 1. And so we get x equals 6 and x equals negative 1. Now, those would be my solution if this was an equation. However, here's where it differs. We have an inequality. So if I go back to these steps, again, we multiplied by the LCD in step 3. Step 4, we simplified. 5, we actually solved that resulting equation. Step 6 and 7 is what's new. On step 6, we need to create a number line that's broken into intervals using the solutions you found and using the excluded values. So what are those? Those excluded values was just one of them. It was 2. And then my solutions were 6 and negative 1. So I'm going to create a number line, excuse me, with those values. So we have negative 1, we have 2, and we have 6. And what we're going to do is we are going to test points within those different regions. So technically we have 4 different points. We need to 4 different regions. So we're going to first check something in this region where I'm putting an arrow. What that means is you'll take any test point that is less than negative 1 and plug it into the original equation. So I'm going to do that. Now I'm just going to do it out for one of them just for time purposes, but I'll explain all of them. So for instance here, maybe we want to test negative 3. Okay, so if I test negative 3, I would plug that into my equation. So that would be negative 3 over 3 minus 1 over negative 3 minus 2 is less than negative 3 plus 1 all over 4. When I simplify that, I get negative 1, and this will end up becoming plus 1/5, right? Because it'll become a negative negative, is less than negative 2/4. If I simplify that, that is really saying negative 4/5 is less than negative 1/2. So my question is that true? Is negative 4/5 smaller than negative 1/2? It is, right? Negative 4/5 is actually a bigger negative number, and the more negative we are, the smaller we are. So this is a true statement. So what that means is that I am true when I am less than negative 1. So now what you're going to do is you're going to put a test value in between negative 1 and 2. I would go with probably 0, right? So I'm just going to do that out loud with you. When we plug in 0, okay, we're simply going to get 0 in the first fraction, then minus negative 1/2, which is plus 1/2, and then we'll get 1/4 on the right-hand side. So it would be saying, is 1/2 less than 1/4? No, 1/2 is greater than 1/4. So that would be false. Now I do another test point. So I'll do it between 2 and 6. Let's take 4. It doesn't matter. You could pick 3. You could pick 5. If you want to make life hard on yourself, you could pick 5.7. I'm going to pick 4. So when I plug 4 into my original inequality, I end up with 5/6 is less than 5/4. Well, 5/6, yes, is less than 5/4. So this is true. Again, you'll probably want to do this out for each one, like I did with the test point of x equals -3, but just for time and listening wise, I'm doing it out loud. And lastly, we're going to pick a test point beyond 6. So that could be 7, 8, 9, 10, whatever you'd like. I'm going to pick 8. When we plug 8 in, we get 30 twelfths is less than 27 twelfths. Clearly, 30 twelfths is more than 27 twelfths. So that would be false. Why that's important is that then that gives you your actual answer. So I am true for all values that are less than -1. So I'm going to use blue now. True for all values that are less than -1. And I'm true for all values that are in between 2 and 6. Now remember, the original problem did not have an equals to, so we don't want to put equals to. So my solution is the following: x such that x is less than -1, or such that it is between 2 and 6. Now, that seems pretty tedious. And the more solutions you have and the more excluded values you have, yes, the more tedious it is because there's more intervals to check on your number line. If you only have one solution and one excluded value, then you have less intervals to check. Okay, so you try number 7.